Hello friends, welcome to Gradify. I am Arham Doshi and let's get started. In this video, we will be learning about two important functions called lower bound and upper bound. Okay. So one important use of binary search is to find where the value of function changes. So now let's say we have a function f of x. It returns true if the value of x is greater than or equal to k, and if the value of x is less than k, we will return false. So if we plot x versus f of x uh, line, then for all the indices till k minus 1, we will have the value of function to be false. Okay, and at this particular instance, from here on we will have the value true, and here you are asked to find the value of x where value of the function changes. At this point the value of function changes from false to true. So how can you do it? Okay, and we don't know what the k is. We just know there is a function, and we can give it input x and we'll give some output, and at particular position its value will change from false to true. Okay, so here one thing we can do is we can start with the number 0. We can iterate through all the numbers from 0 1 2 and until we find false we'll just keep on moving forward, and if we find the value true we'll just stop it. Okay, so it would be like this. For I from 0 to, let's say we have n possible values, and if the function of I is equal to true, then like return I. Okay, and the time complexity of this would be of n. So can we improve it? Now to solve such kind of problem we can use binary search. Okay, we can start with a particular range. We want to find minimum value where f of x is equal to true. Okay, so in the starting we'll be having pointers L and R, and we can like start with mid, and if the value of mid is like false, then we know that our minimum value will be to right of it. So at this point we can do decrease the range, that is we can make this as a range, and in this case this is L, so L would be equal to mid plus 1. Okay, now we will again find the mid element, that would be like this, and if it is like true then we have already found our answer. Okay, so this is one possible answer, but is it like minimum? So no. So there can be more answer in the left side, so we can allocate the answer to this position, and we can like again minimize the range here, and at this point we will set the value of r to be equal to mid minus 1, and we will again check whether this is our answer. We will know that this is also true, so from already existing answer we will just update the answer. So we can keep on doing this. If we find our answer to be false we can go to the right. If we find our answer to be true we can like set the answer, plus we can go to the left, and at the end we will find the minimum position. Okay, and the complexity of this solution is log n, that is much better than the of n solution which we were doing from iterating the array. So now understand about the two functions, lower bound and upper bound. Lower bound is nothing but the smallest index I, such that the value of arr I is greater than or equal to x. So if we see here, we are given an array arr and we are given an integer x, and we want to find the smallest index where value of that element in the array is greater than or equal to 9. Okay, so the first element that is greater than or equal to 9 is this element. So index of this is 2. So in our case answer of the lower bound is 2. Let's see what upper bound is. Upper bound is nothing but the smallest index I in the array where element is strictly greater than x. So focus on the word strictly here. We want to find index such that its value is greater than x, and it should be the smallest value. So if we look here, is this greater than x, is this greater than x? No, 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 no. But this is the first index which is greater than x and which is strictly greater than x. So the answer to our upper bound is like 5. Okay. Now talking about lower bound, we need to maintain this inequality. If we apply it to all the elements of the array, this is same as finding at which position the value of function changes from false to true, and it would be like this. So in this case we can do binary search on this inequality, and we can return the position, this minimum position, which is true. Okay. And if we use something similar, then for the case of upper bound we have to maintain this inequality. Okay, so in this case the answer of this inequality would be like this. This also comes down to the question of solving the problem of finding the position, minimum position where the value of function is changing, and in this case we are changing it here. So now let's move on to the coding part. So here I am just taking the input, and I am taking integer n and k, and I am just declaring the vector v in which I am taking elements. Okay, I am just printing, now I am just printing the content of the vector, that is like this 33999, and I will be writing my binary, my lower bound function, which will take two arguments, vector and the element x. So it would be like this. I will be going from 0 to size of vector -1, that is from beginning to end. At first this would be my range, and I will be initializing my answer to -1. So the answer would be -1 if all the elements were less than our answer. Okay, so and in this case, if this is the same inequality, we will be finding mid, and if the value of mid is greater than or equal to x, then we will just set the answer and we'll move the range to the left side. So that is nothing but we have found our answer. Let's say in this case we have found our answer t here, and we will set the index 6 to our answer, and we will just decrease the range this side. Okay, and otherwise we will be decreasing the range this side, that is nothing but l equal to mid plus 1 by 2, and after that we will return the answer, and answer would be the smallest such index. So if I run the function, it is telling that the lower bound of 9 is 2, that is 0 1 and 2, that is this position. So it is giving me correct answer. So let's see about upper bound. So only one change here was this. So I will be updating answer only when the value of the array is greater than x. So, and if the value of array is less than x, then our answer would be at the right side. In the end we will be returning the answer. Okay, so we can see here that 5 is the position of upper bound, that is this value, that is the value just greater than the 9. Okay, so we can also do this using the inbuilt function of lower bound. The inbuilt function takes three arguments, that is the pointer to the start of the container, pointer to the end of the container, and the value that we want to query. Okay, and this lower bound works only with vectors and array, because in that case the pointers are monotonically increasing. Okay, So we can just find, it will give us the pointer to the position where x is greater than or equal to 9. So it will give us pointer to this position. We can just subtract it to the starting value, that is this pointer, and we will just convert it into integer, and this will basically give us the index of that particular element. That is, in this case we will get the pointer to here, we will subtract it to the pointer, that is like to the 3, and this will give us the index, that would be 2. We'll be doing something similar with the upper bound. It will give us the index of the element that is just greater than 9, that is 10. So this is our answer. So now let's discuss an interesting question. The question is, find the number of occurrence of, let's say, value x, and in this case x is equal to 9. So in this case what we can do is, we can first try with the brute force approach, in which you will be maintaining count variable which would be 0, and we can traverse from to all the indices, and wherever we will find x, then we can like do count plus plus, and it will like take off n time, but we can solve it easily by using lower bound and upper bound. So when we find the upper bound, it will give us the value this, that is 5, and when we do the lower bound, it will give us the value this, that is like 2. We can just subtract both the indices, and the subtraction of this will give us the number of occurrences of 9, that is, this is nothing but upper bound minus lower bound. So this is one such interesting problem that can be solved by upper bound and lower bound. So thank you friends for watching. If you like the content, smash the like button, and until next time, goodbye.